Hello again. Welcome back. We're going to start chapter 3 today. Chapter 3 is all about graphing quantitative data. Remember, in chapter 2, we were talking about graphing categorical data. So now we're going to be moving to quantitative data, which again is data that can take on any real number, right? Basically from 0 to infinity. So one main way we like to graph or display quantitative data is with histograms. Histograms can tell us a lot about our data. They can provide information, mostly about the type of distribution and about the shape, which we'll talk about in a minute. So notice you might think this looks a bit like a bar graph, which we'll do a side-by-side comparison on one of our next slides. But just to look at this histogram, right, you can see that we have our numbers of employees over here on our vertical axis or our y-axis, right? So think of these as frequencies or counts. And then down here is our quantitative variable, right? Our salary in thousands of dollars, right? So salary can be anything from 0 to, right, hundreds of thousands to millions and billions, right? You can make $51,000, you can make 52,000, you can make 52.5 or 52.3, right? And so on. It can be any real number in between those. So the way to read this histogram is that your salary in thousands of dollars between 0 and 10, right? So between 0 and $10,000 in this example. And then we've got this other kind of cutoff, right, between 10 and 20,000, 20 to 30,000, 30 to 40, 40 to 50, 50 to 60, right, and so on. And so if we come over to the 0 to 10, then we can say, based on this bar, right, maybe about 50 of our employees make less than $10,000, right, make between 0 and 10,000. Whereas if we come between 10 and 20, we can say that almost exactly 300 of our employees make between 10 and 20,000, right? So this kind of shows you the distribution of these salaries of your employees. You can see most of your employees make between 40 and 50, right? Very few make between 0 and 10, even fewer make between 90 and 100, right? And so on. All right, so histograms versus bar charts, again, they look the same. The usage, right, of a bar chart here in this first row is to compare different categories of data, right? Whereas a histogram is to display the distribution. So in a bar chart, each of your bars is a different category. Whereas in the histogram, each bar is a kind of its own little range within the total range of values that you can have. The type of variable, right, in a bar chart is obviously categorical and histogram is numeric. The rendering, or just kind of how it looks, the bar chart, right, each data point is a separate bar, right? Those bars aren't touching. And in a histogram, the data points are grouped and rendered based on the bin value, bin being each of those bars in the histogram. The entire range of data is divided into a series of non-overlapping intervals, which is how we kind of set how thick those bars are, right? So we had 0 to 10, 10 to 20. We'll talk about that later when we create our own histogram. The spaces between bars, right? The bar charts will have space. Histograms should not have space, right? This is important because our intervals, unless there's no employees, right, that fell between one of those categories, the salaries touch each other, right? They butt up against one another. So there's no space in between them. We didn't say our first category was 0 to 9,999. and then left a little space for 10,000, and then our next space was 10,001 to so on, right? There's no spaces in between. It's a continuous interval. In a bar chart, you can reorder your bars, right? If I have a category of eye color, right, I can put people with blue eyes first, and then brown, and then green, or I could do green, brown, and blue. The order doesn't really matter too much in bar charts, but your histograms, the order has to stay the same, right? It's following the numerical order. You can't start with 50,000 here and then jump to 100 and then down to 10,000 and so on. It wouldn't make sense. Okay, so just visually write a bar graph versus a histogram. Here in our bar graph, right, we have different categories for a categorical variable of language, right? We have Spanish, Chinese, and so on, right? There's spaces between our bars. So here we can see that almost 50 people speak Spanish, about 60 or so speak Chinese, and so on. Whereas and these are counts of those language speakers, right? Whereas in our histogram here, our continuous quantitative variable is years, right? And then what we're measuring is GDP in percentage. So here between 1960 and 1965, the GDP percentage, right, of whatever country this is was 60%, right? You can see it increased over time, then decreased, and then went back up. So again, you couldn't move 1980 to 85 here. It just wouldn't make sense to start with a later year and then go back in time, right? And again, these bars are touching, right? Time is continuous. There's no gap between 1960 and 1965 and so on, right? So these bars are touching. Okay, so the histograms and really graphing quantitative data with other forms of graphs, we're really interested in three main things: the shape, center, and spread of our data. And so graphing this data can help us see this quite easily. The first thing is shape, and this can mostly be three different things. It can be unimodal, bimodal, or multimodal. And so the question here is how many humps or how many peaks really does the data have, right? Not necessarily just the peak itself, right? But you want to see that whole kind of hump, so to speak. So we would say this histogram, and really this data set that makes this histogram, right, is bimodal. So bimodal means it has two distinctive humps. If we were to cut this graph in half and only look at the values from 1 through 9 and ignore 10 to 19, we would say it's unimodal, right? If it only had one hump, uni for 1, and then multimodal would be if it had a third, fourth, fifth, sixth hump, and so on, if it just kept going, right? If it followed this pattern between 20 and 30 and so on, if it goes up and down, and then it went up again out here and down again, it would be called multimodal. This is another example of a histogram. This one we would call uniform, roughly uniform, right? It doesn't stay, it has no major humps, right? It doesn't go up and down. It stays fairly consistent over time. So again, this is what we would call uniform. Okay, so a little more on shape. From a histogram, we can also tell if our data is symmetric, right? And so what this means is that it's balanced on the left and the right side compared to the middle. right? We call the left and the right, we often call these the tails of our histogram or the tails of our distribution. So think if you could put a line right down the center, right? Just like in art class, if you could flip that image or this histogram in half, fold it in half, would it look the exact same right on one side as it does the other? Would each sides be exactly equal? You can tell this one is, right, the exact same. Yeah. And so when our histogram is symmetric, when our distribution is symmetric, we can say that the mean or the average of our data, right, of our distribution of data is approximately equal to the median. We'll talk about what these things are a little later and how to calculate them, but just know that when you have a symmetric distribution, a symmetric data set, then your mean and your median are approximately equal. And that they'll be approximately at the center of your histogram or your data as well. Okay, so more shapes. You can also have a skewed right distribution or right skewed, either way you want to think about it. If your distribution is skewed right, you have values that go far out to the right of your distribution, right? This right tail that we talked about in the last slide is kind of long, but it's not very tall, right? So you can see most of your data based on the frequency, most of your data has high frequency right around here, and then you have a very few number or very few frequency of very large values that go out to the right. So if you see distributions that look like this, it's called skewed right. And same thing for skewed left, right? Most of your very high frequencies come out here, or out here to the very right of your distribution, right? But you have a very small number, it's pretty hard to see in this, but you have a very small number of values in this case that are smaller, right, than the rest of your distribution. So this creates a long tail, right, a left tail, which is why we call this skewed left. Okay, so we talked about shape. Now let's talk about center. One way we like to measure the center is with the median. And the median is the middle value that divides any data set into two equal parts. One easy way to see this is with a stem and leaf plot. We'll talk about stem and leaf plots in a minute. While I have it up here, you can kind of see the stem is the base 10 of your number, whereas the leaf is the single value to the right of your number, right? So for my stems, I've got, think of this as 10s, 20s, 30s, and 40s, right? So the stem is that first number to the left, right here. I've got 15, a 16, 21, 23, and so on. I've got a 30, a 32, and a 41. So I'll take all the stems, right, or the first numbers, all those unique values, 1, 2, 3, and 4, and I've put those here in my stem. And then in the leaves, I'll add the value on the right of each number, right? So I have a 15 and a 16, so I've added a 5 and a 6. So this 1 and 5 together, that makes a 15. The 1 and the 6, right? That shows it's a 16. And likewise here, right? For this 21, I've got a 2 and a 1. That's my 21. I've got two 23s and two 26s, right? So I've put two 3s here for 2 23s and 2 26s, and so on. So to find the median, we want to find the middle number, right? The middle value that divides any set of data into two equal parts. So if we want to find the number that divides it into two equal parts, what we can do is first line our data up. This is a very important part, from least to greatest. So this data set is already done for us, right? It starts at 15, which is the smallest. It goes up incrementally 16, 21. It's always increasing, right? As we go to the right, it's not increasing, it's staying the same because we have more than one of those numbers. So if I wanted to find the median of this data set, all I could do was just start crossing out, right? I'm looking for the number in the middle. So to do that, I just start crossing out the numbers at the end, right, until we get to the very middle. And uh-oh, I'm left with two numbers, right? So I need a number in between these two numbers that will cut this data in half, right? So that means I'll have 1, 2, 3, 4, 5 numbers on the left and 1, 2, 3, 4, 5 numbers on the right. And we don't just want to pick any number in between, right? 24 or so. What we do to find this is we add these last two numbers that we're left with together. So I'll add 23 plus 26, and I just divide it by the number of numbers I'm adding together, which is 2, right? So I'll divide it by 2. And this is 49 divided by 2, and that is 24.5. So basically 24.5 is exactly in between 23 and 26, right? So 24.5, you add 1.5 to get from 23 to 24.5, subtract 1.5 to get from 26 to 24.5. So this number would be our median in this case for this data set. Okay, our spread, right? This is how spread out is our data, how far apart is it, how close together is it, and so on. There's a few ways that we can measure the spread of our data. We can take the range, which is just the maximum value, subtract it from the minimum value, right, to get our range. There's something else called a 5-number summary. This consists of the minimum value and the maximum value, right, which is what we've used to calculate our range. So the smallest value in the data set and the largest value in the data set. It also consists of Q1, Q2, which is actually our median, and our Q3. So Q1 is 1/4 is the cutoff such that 1/4 of the data lies below this value. The median, remember, was the cutoff value such that half of the data lied below, the other half was above. So now think of taking the median, right? If half is below, half is above, cut the median in half again, right? And find the number that cuts off from your minimum value to the median. And that cutoff value will be your Q1. We'll do that together and find that. Likewise with Q3, right? This is 3/4 now of your data is below this cutoff and 1/4 remains above. So now again, think of starting at the median at the bottom and your max at the top. Find the number, just like we did with the median, that cuts that set of data in half, and that will be your Q3. We talked about the max, right? This is the largest value in our data set. And then we have the interquartile range. This is just Q3 minus Q1, and we'll use this later on in the chapter. Okay, so box plots are another good way to graph or display quantitative data. Box plots are good at showing the spread of your data. They're also good at showing the distribution. So the box plot is actually made up of those quartiles, excuse me, we were just talking about. You can see the box itself, the beginning of the box, right, is made up of your Q1, or the 25th percentile as we call it. And then the closing of the box, right, the end of the box here is made up of our Q3, which is our 75th percentile. And then we draw another vertical line inside of our box, which denotes our median. So the size of this box, right, would be our IQR, so we can get a feel for how big that is by how big the box is. And then we draw another set of vertical lines at our minimum value and our maximum value, excluding any outliers, right? So you can see here, we actually had values smaller, but they were marked as outliers with these little green circles. And we'll talk about this in a later video for how to calculate outliers. But we'll use that IQR to calculate our outliers. Anything less than Q1 minus 1.5 times the IQR would be called a lower outlier. Anything greater than Q3 plus 1.5 times our IQR would be considered an upper outlier. So when you have upper and lower outliers, you want to denote them on your box plot, and then you want to leave these, we call them kind of whiskers, right? The line that connects to your box and that you draw a line at is the smallest non-outlier value. And the upper whisker is going to be the largest non-outlier value as well. So here I just kind of like this slide to kind of show you the differences and similarities between a histogram and a box and whisker plot, right? So here we have a pretty symmetric distribution, right? This value looks like he's a little farther out. It's not perfectly symmetric, right? But you can tell from our box plot, right? These whiskers are kind of the same length. The box is a little larger, right? But you can also see the median here isn't perfectly in the center of our box, right? If the median is exactly in the center of the box, that would show a more symmetric distribution like we have on this right-hand side, right? It's still not perfectly symmetric. We've got a couple bumps along the road, but you can see that these values are much more, really the box plot itself, right, is more symmetric, right? The line looks like it's a little closer to the middle, maybe still not perfect again. This one has an outlier as well, right? Whereas this one does not. But really compare these two up here down to these skewed distributions, right? We've got positive and negative. Remember, this is right skewed because we've got these this right tail here, and this is left skewed out here. We've got this left tail. So now look at this box plot, right? Look at how our Q1 is smushed all the way here because we have so many frequencies, right? So much data. We have over 40 counts of values between 0 and 0.5, right? So between 0 and 0.5 here is what? It's half of our data, right? With our median. The median is the cutoff for half of our data. So up here, the median was at 0 because our data was much more spread out, right? Whereas now our data is much more congested between 0 and zero point 0.5. The majority of our data, half of it, is between 0 and zero point 0.5. And then the rest of our data, right, is spread out between zero point 0.5 and 4. Same thing on this side, except now the majority of our data is squished in between 6 and 7, right? So you can see whether it's the first 50% or the second 50%, if this is where our median is, right? 50% of our data, again, is smushed up here between 6 and 7, and the rest of it goes from about 0 to 6.